Hey guys, welcome to this talk on conic sections. This is traditionally a topic that's taught or covered at the beginning of pre-calculus, but I think it's best to start our discussion of Calc 3 with it. So let's get going. All right, so the term conic sections comes from intersection of a plane with two cones that are put on top of each other tip to tip. So that's what that means, that if you have, this cone on top and then this cone on the bottom, the two tips are on top of each other. Now, if we take this plane, so imagine that to be a sheet of paper, something very sharp that you can push through different objects. So imagine taking the sheet of paper and pushing it through the top of the cone into the body of the cone. Now, the path that this cutting action will trace out is going to be a parabola. Now, what happens if we take the same plane or the same very smart sheet of paper, but instead of cutting it through the top, we go in through the side? Well, when we do that, we're always going to end up with an ellipse. As long as we go at an angle, it's going to result in an ellipse. Now, if we take that same exact point of entry, so this point right here, but instead we go exactly perpendicular to the axis of rotation for a cone or an axis of symmetry for a cone, that will create a circle because we're not coming in at an angle, so it's going to go completely straight across. And on the other hand, if the angle is completely vertical, so if we go through the top and we go straight down, instead of going at an angle, we go straight down, that's going to result in a hyperbola or two parabolas. You can kind of sort of think about it. It's not really a technical way to think about it, but you can imagine that if you cut two cones vertically, the plane is going to intersect or create two parabolas. Again, just think about. Now, the bottom row of shapes that we have here are actually degenerate cases. Those only ever happen when the plane that we're passing through this conical section is passing through the origin. So if we pass our plane or our laser paper right through where the two cones touch each other, we're going to get a point. Now, what happens if we take the plane and we run it right across the edge or along the edge of the first cone, and because of the symmetry of the argument, it would go down the edge of the other cone as well. This will result in a straight line. And finally, if we take this plane and basically orient it vertically and go straight through up and down the origin, then we're going to end up getting two separate lines, two crisscrossing straight lines. Now, the equation of all of these conic sections, each one of these 7 shapes, can be given by this general equation: ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. All of the conic sections come from making some of these coefficients, a, b, c, d, and e and f, 0. For instance, if we kept ax squared, made b 0, so that means that this term would go away, and we made c 0 as well, so that means this goes away, and we make e 0. So what you're going to be left with is ax squared plus dx plus f equals 0. Well, that's just the equation of a parabola. You might have seen it as ax squared plus bx plus c equals 0. But remember that these constants, these coefficients, are arbitrary. They can assume any number, and also any variable or any letter. So you could have rearranged these, but canonically, we say that this is the equation in standard form of any conic section. So let's start looking at these in more detail. We start with a discussion of parabolas. Now, a parabola is created when you take the locus, or a collection, of all the points that are equidistant from a focus and directrix. So let's take a look at a graph just to see how this behaves. So if we look at this, what I want you to concentrate on is the distance from this point, which is called the focus of the parabola, to the point on the graph, versus the distance from the point on the graph to this red line called the directrix. So if I press play, Oops, gotta press play here. You'll notice that the distance between the 2 points never changes. When it comes back around, let's pause it here for a second. So if we look at the distance from the focal point to the function right there, and then from the function to the directrix, which is down here, then those distances are always going to be the same. Let's press play just to see that it happens. Now, the distance between the focal point and the vertex of the parabola is the same as the distance between the vertex of the parabola and the directrix. Later on, we're going to assign this distance p. And then the same thing happens as the curve sweeps to the other side. Coming back here, let's formalize things with a bit of algebra. The equation of a parabola that opens up, that's what this indicates, that has a vertical line of symmetry. With any vertex, h comma k, on the Cartesian coordinate plane, the equation of the directrix is given by y equals k minus p. And again, we'll talk about this in a bit, but the idea again is that if you take the y coordinate of the vertex and you move that distance p away from it, you're going to end up with the equation of the directrix. Now, the equation of the parabola in standard form is y equals 1 over 4p times x minus h, which is the x coordinate of the vertex, the quantity squared, plus k. K is the y coordinate of the vertex. Now, whenever we have a parabola that opens up, the focus is always at h comma k plus p. So again, remember that the focus and the directrix are at equal distances from the vertex of the parabola. So in order to get to the directrix, we subtract p. In order to get to the foci or the focus point, we add p. Similarly, if we were to look at the equation of a sideways opening parabola, a parabola with a horizontal axis of symmetry, the vertex is in the same general spot. Now here, the directrix, instead of it being y equals h minus p, the directrix is always perpendicular to the axis of symmetry. So if the axis of symmetry is horizontal, the directrix is going to be a vertical line. Here, just like we did before, we subtract p. And in standard form, the equation of the parabola then becomes x equals, notice this is not y equals, it's x equals 1 over 4p, this is the same, y minus k, the quantity squared, where k is the y coordinate of the vertex, plus h, where h is the x coordinate of the vertex. And in this scenario, or in this setup, the focus is at h plus p comma k. Again, in order to get to the directrix, we subtract p. In order to get to the focus, we add p. Now, a question that I want you to consider and think deeply about is, must p be positive? I haven't said anything about restrictions on what p can assume. So p could potentially be a positive number or not, and that's the question I want to ask. Could it be negative? Could it be 0? Could it be a decimal? Does it have to be a whole number? Could it be a rational number? Could it be an irrational number? Could it be like pi or a transcendental number like e? So are there any restrictions on the value of p? And if there are restrictions, what are they? What can p not be? The answer is quite simple. I just want you to think about it, pause the video if you need to, and then come back in a bit. Now, the derivations of these formulas, if you're taking my Calculus 3 course, they're in the textbook and they're left as exercises. So please make sure that you know the proofs of these very, very simple formulas. The derivations are quite simple. Calculus 3 is a very rigorous course, and it helps a lot when you know some basic proof techniques. So let's move on to a couple of examples. So let's say we're asked to find the equation of the parabola with a focus at 1, 2 and directrix at y equals 3. So here, it's best to always draw a picture first. So my parabola has a focal point at 1, comma 2. So that's my point right there. And then it also has a directrix at y equals 3. Now, the parabola will always open away from the directrix and towards the focal point. So it has to point down, or it has to open downwards. However, even with it opening downwards, we know that if it opens downwards, there's still going to be a vertical line of symmetry, or vertical axis of symmetry. Remember that the vertex is the same distance away from the directrix as it is from the focal point. So if we find the distance between the focal point and the directrix and cut it in half, that's exactly, or we find the midpoint, that's exactly where the vertex of the parabola is going to be. So in this case, that point halfway between 1, comma 2 and 3, comma 2, or sorry, 1, comma 2 and 1, comma 3 would be 1, comma 2.5. 2.5 is halfway between 2 and 3. So if I know what my vertex is, I can figure out what my p-value is. Remember that p is the distance from the directrix to the vertex, or the vertex to the foci. Now, if my vertex is 2.5 and I have to get to 3, 2.5 minus 3 is going to give me negative 0.5. So that is what is going to replace p in the equation with. So we get 1 over 4 times negative 0.5 times x minus h. The vertex x coordinate is just 1, so that goes there. The quantity squared plus 2.5, which is the y coordinate of the vertex. Now 4 times negative 0.5 is just the negative 1/2, and the rest of it stays the same. One very strong piece of advice I would have or give to you for this term: if you're studying Calculus 3, whether you're taking my class or not, always, always, always graph every single function you come across. Rotate it around, play with it in GeoGebra or any other 3D plotter that you may have access to, perhaps Maple, MATLAB, Minitab. A lot of these algebra packages or computer algebra systems will graph 3D plots for you. Get a feel for what these functions look like in three-dimensional space, and it's going to help you immensely when it comes time to visualizing functions later. Now, one last thing before I move on. The leading coefficient being negative for a parabola always indicated that it opened downwards, so all of this kind of has to fit together. We can't have a parabola opening downwards, but then having a coefficient that's positive. So all the different pieces of information have to connect together. Moving on to the next example, we take the exact opposite approach. Here, we give you the equation of the parabola, x equals 1/8 y squared minus y plus 1, but you're asked to find the focus and the directrix of the parabola. And then there's another part to the question, and it asks us to verify that 7, 12 is equidistant from the focus and the directrix. That means this point has the same distance from the focus as it does to the distance to the directrix. So let's start with finding the focus and the directrix of the parabola first. In order to do that, we need to get this equation to look like this, which is the standard form of the equation of a parabola. This can most easily be accomplished by completing the square. If you're not sure of how to do that, pause the video, go on YouTube. I'm sure there's 1,000 videos on how to complete the square. The one thing that I find that most students will make a mistake on is that they complete the square with a non-unit leading coefficient. The leading coefficient is the coefficient of the degree term. So this y squared has to have a coefficient of 1. Otherwise, there's this usual trick that we use for the most part. That trick doesn't work. So if we were to factor out a 1/8 from the first two terms, we leave the constant term as it is, and you'll see later why. But if I factor out a 1/8 from the first term and from the second term, I'm going to get y squared minus 8y. You might not be used to doing this, so make sure you pause the video, make sure you understand how exactly this happened. And if you're not certain of it, distribute and understand why you would have an 8 here. Now, once the leading coefficient is 1, you can divide the middle term, 8, by 2. So 8 divided by 2 would be 4. Square that, you get 16. Now, we can't simply just add 16 to a problem. That's going to change it. We cannot change the problem we're given. However, we can make it look different. That's different from changing. You can put on a hat. You're still the same person. You just change the way you look. So I need to add 16 to make this a perfect square. But in order to do that, I also have to subtract 16 simultaneously. And the reason we do that is so that the equation or the function that we're playing with doesn't change. If we add 16 to a quantity and then subtract it immediately, we're really just adding 0. Adding 0 changes absolutely nothing. So that's a legal step. We can do that. Now, the next clever part of this trick is that we take the first 3 terms, the 3 terms that make a perfect square, and we distribute 1/8 into that consolidated term. So we keep this y squared minus 8y plus 16 together as it is. But then we peel off this last extra term. So 1/8 times negative 16 comes across on the outside. We're doing very specific partial distribution. We're not distributing it to these 3 terms, but we are distributing it to the last one. Now, 1/8 times 16 is going to give us a 2, and everything else stays the same. However, recognize that this is a perfect square, and it's the square of y minus 4. If you're not sure of this, FOIL this out and convince yourself that you really do get y squared minus 8y plus 16. Once we're at this stage, we can combine like terms. So negative 2 plus 1 is just negative 1. And at this stage, we're basically done. We can rewrite 8 as 4 times 2 to make it easier to identify what p is. But remember that this component that's always attached to y is the y-coordinate of the vertex. So the y-coordinate of the vertex will be 4. The x-coordinate of the vertex in this form will be negative 1. So that's exactly what this information states, that p must be 2, h must be negative 1, and k must be 4. So at this stage, we have the vertex. If we add p to the vertex, we're going to get to the focus, and if we subtract p, we're going to get to the directrix. Now the question always becomes, well, do we add it to the x-coordinate or to the y-coordinate? Short answer is look for your axis of symmetry first. In this case, remember that we started with x equals, and then it was a function of y. So this means this is a side opening parabola, or it opens sideways. It might open to the left or it might open to the right. That's immaterial to us. The only thing we care about here from that discussion is that the axis of symmetry is a horizontal line. The axis of symmetry is where the vertex and the focal point have to live. They have to live on that particular line. So if the axis of symmetry is a horizontal line, the focal point is going to be to the left or to the right of the vertex. It can't be above or below. So since it has to be to the left or to the right, we add it to the x-coordinate. Similarly, the directrix is always going to be to the left or to the right as well. So we subtracted rather from the x-coordinate of the vertex. So when we do that, the focal point turns out to be 1, 4, and the directrix turns out to be x equals negative 3, the equation of a vertical line. So now that basically is it. The question asked us first to find the focus and the directrix. We just did that right here. We found the coordinates of the focus, 1, 4. We found the equation of the directrix, x equals negative 3. Now, for the last part, we needed to verify if this point 7, 12 was equidistant from the directrix and from the focal point. So let's label a couple of things. Let's call this point P, just so that it's easier to talk about it. Let's talk about the focal point 1, 4 as Q, and let's label a new point R as negative 3, 12. Pause this video, take a moment, make a picture perhaps, and figure out where exactly this point came from. It's not a very deep result, but it's something that needs to click for you independently. So I'm not going to give that away. Pause the video, come back to it when you're ready. Now, the distance between the 2 points P and R is 10. And hopefully you've drawn a picture when you were thinking about where this point came from. And this note really should just say, look at your picture and determine why that distance is 10. If you're not convinced, just use the distance formula between P and R, and you should get your answer as 10 as well. Now, for the distance between P and Q, we do use the distance formula. x2 minus x1, the quantity squared, plus y2 minus y1, the quantity squared, all raised to the 1/2, or square root of the whole thing. And if we plug in the numbers where they belong, we end up with 10 again. And that's exactly what we set out to prove. We were trying to verify that the distance between the points PQ, which is the point 7, 12, and Q was our focal point, is the same as the distance between the point 7, 12 and where the directrix is. If this point is equidistant from the focal point and from the directrix, what does that mean about that point? I forgot to write that question down, but I want you to think about that as well. So if a point is equidistant from a focal point and a directrix of a parabola, what does that mean for that point? Next, we move to ellipses. So ellipses are a locus of all the points, or a collection of all the points, where if you were to add the sum of the distance from a focal point to a point on the curve to the distance between the other focal point, that sum will always be the same. So if I could draw a couple of things, let's say from this focal point, we go to this point and we go there. That sum will be the same as the distance from here to here, and that's going to be the same as the distance from here to here. If we were to add these two arcs, that sum will always be the same. So if you were to draw all the points where that happens or where that's possible, you're going to get the graph of an ellipse. Let's take a look at this very quickly. Everything is backwards on my screen, so it's hard to... All right. So you'll notice that the sum can be forced to be the same by putting these two thumbtacks on paper, putting a piece of string between them, and then running your pencil in circles. This forces the pencil to the sum of the distance between the focal point and where the tip of the pencil is to always add up to be the same number. Coming back here, a couple more labelings. So the focal points here are right here and right here. Those are the white points. The orange ones are called the vertices. The vertices always lie across or along the major axis. So the major axis is essentially which way is the ellipse stretched? Is it stretched horizontally or is it stretched vertically? So if it's stretched horizontally, you're pulling it to the side. If it's stretched vertically, you're pulling it up and down. The distance from the center to one of the vertices is called A. And if we were to find the distance between the vertex and another vertex, you're going to end up with 2A, twice the distance. Similarly, if we take the distance from the center along the minor axis to the vertex here, it's going to be B. And if we take the distance between this vertex and this one, you're going to get 2B, twice that distance. So major axis in this case is horizontal, minor axis is vertical. So we have two standard equations as well, just like we did with parabolas. There's two scenarios that we can have. We can either have a horizontal major axis or we can have a vertical major axis. If we have a horizontal major axis, that means the ellipse is laying down. The major axis is going side to side. Excuse me. Then the equation is x minus h, the quantity squared, all over a squared, plus y minus k, the quantity squared, all over b squared equals 1. It always is going to be in this form, and it's always going to be 1 on one side of the equation, and it's always going to be a sum on the other side. Now, you'll notice that for a vertical major axis, the denominators switch locations. The numerators stay the same, but whenever you're dealing with a vertical major axis, the a squared, which is the distance on the major axis goes under the y term, because here the distance from the center up here would be a. Please make sure you memorize these two equations and, well, any other equations that you're presented with. Just like with the parabola, the foci, in this case there's two of them, lie along the major axis. C units from the center, where C is, this should be a square. Let me fix it very quickly. C squared is equal to A squared minus B squared. So let's say we're given the graph of an ellipse and we're asked to translate that into an algebraic equation for it, similar to the types that we saw earlier. So in this case, we can start looking at the center first. The center is at -3, 1. So we write that down. The vertex is up here, so -3, 6, and -3, -4. So we write those two pieces of information down next. It's stretched vertically, so it's going to have a vertical major axis. A will therefore be the distance between this point, the center, and one of the vertices. So 6 minus 1 is going to give us 5. So that's what A is. B is the distance in the other direction. So this portion is 2. So B turns out to be 2. Now, if we know what A and B are, and we know what our center is, from that we can write down the equation of our ellipse. So we can write x minus h, but h is -3. So two negatives make a positive. X plus 3, the quantity squared, all over 2 squared, which is just 4, plus y minus 1, which is k, the quantity squared, all over 5 squared, which is a, plus 1. And that's the equation of this ellipse in standard form. This one's a little more involved, but let's go through it. So let's say we're asked to find the equation of the ellipse in standard form and then graph it. So oftentimes you'll be given functions that look wonky like this. Don't worry, it's all going to be just fine. So we start with the equation 4x squared plus 9y squared minus 8x minus 36y equals -4. The first thing we do is we rearrange these terms to put the x's together and then put the y's together. So we rewrite it as 4x squared minus 8x plus 9y squared minus 36y equals -4. Now remember, for completing the square, the leading coefficient must be 1. So we have to factor a 4 out of both these terms. And if we do that, we're left with 4 times x squared minus 2x. And from these two terms, we need to factor out a 9. So it becomes 9 times the quantity y squared minus 4y equals the -4. And just like we did earlier, we're going to complete the square now. So divide the middle term by 2, that gives us 1. Square it, that gives us 1. So we add the 1, but then we also subtract the 1 at the same time. For the second expression, we divide 4 by 2, which gives us 2. Square that. That gives us 4 again. So we add 4 and subtract 4. And just like we did earlier, we're going to keep the first 3 terms together because they form a perfect square. So I'm going to leave those exactly as they are. But I'm going to peel off this last term, leaving behind -4 times 1, which is going to give us a -4. Same thing here. We take the first 3 terms, encapsulate them into a single set of parentheses, and keep the 9 in front. But peel off this extra, or this last -4, to get -9 times 4, which is going to give us -36. Now at this stage, we can convert this into a perfect square, which is the square of x minus 1. And this expression is the square of y minus 2. So that turns into y minus 2, the quantity squared. Now remember, this needs to look like x minus h, the quantity squared, over a squared, and the other side of the equation has to be 1. Well, we got to get there. So first, we can get rid of this -4 and -36 and add them over to the right-hand side. The -4 and the +4 will cancel each other out, leaving behind just the 36. Now that we have a term with x squared, a term with y squared with a plus in the middle, and a number on the other side, I can divide all 3 terms of this equation by 36. And when we do that, the 4 and the 36 will go in 9 times, 9 will go into 36 4 times, 36 will cancel each other out. So that equation then cleans up into this whole expression. And this is exactly the equation of an ellipse in standard form. Now from here, we can find what a is. A is the square root of 9 because it's the larger of these two. And since the larger number lives underneath the x term, we know that the horizontal axis is going to be the major one. Had the 9 been underneath the y, then we would have said, oh, this is an ellipse that's stretched vertically. So the center again is still at 1, 2. The a, or half the major axis distance, is 3, and b is 2. Now from here, we can figure out what c is. Remember, c is the distance between the focal point and the vertex. So we use the formula c squared equals a squared minus b squared. We can replace a squared with 9, b squared with 4. 9 minus 4, that's simple, 5. Square root property gives us c equals plus or minus the square root of 5. Now remember, because it's a horizontal major axis, we can only go left or right from the vertex. We can't go up or down, which means we add root 5 and we subtract root 5 from the x coordinate. We have to use the x coordinate because that's a sideways motion, or it's a horizontal translation. It's not going up or down. For the vertices, we do the same thing. We add the distance a to the x-coordinate of the vertex, and we subtract the distance a from the x-coordinate of the vertex. Now at this stage, first start with the center, 1, 2. Plot your focal points, 1 minus root 5 and 1 plus root 5. Now you can plug these into your calculator or just think about it a little bit. Square root of 4 is 2. So square root of 5 has to be a bit more than 2, but it can't be 3 or near 3 because square root of 9 is 3. 5 is much closer to 4 than it is to 9. So it's going to be 2 and some change. Well, 2 and some change plus 1 is going to be 3 and some change. So that's why we're just to the right of 3. The vertices are at negative 2, 2 and at 4, 2. So we plotted those. And then from the center, we can also go 2 units up and 2 units down because that's what b is. And once we have the 4 vertices, we can just connect the dots and say that's our ellipse. So that's how you can graph an ellipse once you have all these individual pieces of information. Now, hopefully you've kind of sort of developed a feeling for if A and B are close together, then you get a more rounded shape, something close to a circle. And if A and B are very, very far away from each other, meaning one is much larger than the other, you're going to get this squishiness. So the eccentricity or the curvature of an ellipse depends on the values of A and B. If A is significantly larger than B, so let's say A is 100 and B is just 1, that means the distance from the center all the way out to the vertex is 100 on the major axis. But on the minor axis, you're only going up by 1. So think about how horizontally stretched that ellipse is going to be. Now, what happens if A is exactly equal to B? So not close to it, but exactly the same. You write down the equation in standard form for an ellipse. Now, if A is equal to B, wouldn't B squared be the same as A squared? Well, if you buy it, we can make the substitution. We can replace B squared with A squared. Now, what happens if we multiply all 3 terms of this equation by A squared? Well, this A squared goes away. This A squared goes away. 1 times A squared will just give us A squared. Take a breather, pause the video, think about what this is the equation of. You might not have seen it with exactly these letters. You might have seen different letters representing constants, but think about what this reminds you of. Pause the video, come back once you've kind of thought about it for a bit. It's actually the equation of a circle. Hopefully you were able to get there. Instead of A, we use R. But remember that constants are arbitrary. We can use R for the radius, we can use A for the radius, we can use P for the radius. We typically don't, but we can. Now, Whenever we have a circle, the center and the focal points are exactly the same. These aren't different like they are for an ellipse. And the radius is r. There is a formula for eccentricity to figure out numerically how round something is. And the eccentricity is always represented by lowercase e, and it's always the ratio between c and a, which is called the focal length sometimes, and a is the major axis divided by 2. This is a measure of how non-circular something is. So how much does it deviate from this perfect circular shape is what we're trying to figure out. So if there is no deviation because you're exactly what a circle is supposed to be, then the eccentricity is 0. There are no deviations. So it's just the 0. There's nothing else to it. On the other hand, what happens if we stretch it out or if we squish it down? Well, then we deviate significantly from a circle. In that case, you get a higher number, 0.9. So this is very non-circular. This is extremely circular, so that's why it's 0. Now, if E is exactly 0, you get a circle. But this inequality indicates that E has to be less than 1, and it can't ever be equal to 1. I want you to think about what would happen if E were 1. So again, pause the video. I'm not giving answers to these questions. Think deeply. Maybe draw some pictures, write out some algebraic expressions, plug in some numbers, try to play around with some equations, create equations, or try to, where C and A are the same. If C and A are the same, that's exactly how you're going to get 1 for the eccentricity. So determine why that's not possible. Why is it that I would write less than and not less than or equal to 1 for the eccentricity? The last topic for this section is hyperbolas. So very, very roughly, and I'm going to put maybe air quotes around this to say that this is not exactly a very specific definition, but you can kind of sort of remember it that way as a memory aid or a memory tool. Ellipses they have a positive sign in the middle because they're the sum of the two terms. Now, if you take the exact same formula, but you stick it with a minus in the middle, then it becomes a hyperbola for one of the scenarios. So it's not always going to work, but remember that ellipses always have to have a sum of two quantities. Hyperbolas have to have always a difference of two quantities. It has to be the case. Now, a hyperbola is defined as the locus of all points where the absolute value of the difference or the distance from the foci is constant. So let's again look at a picture, or in fact, a video of this. So what you should observe here is the distance between the two focal points. So this is one focal point, and this is another focal point. If you take the distance between this point and the point on the curve, which is right here, and then you take the distance from this point to this focal point, those are going to give you two distances. If you find the difference between them, if you do the big distance minus the small distance, that answer is always the same. So as we play this video, if I were to find the distance between the focal point right here and this point, oops, going the wrong way, and the point on the curve, let's say that that distance is 10. Now from that point down here to this focal point, let's say that the distance is 2. So the difference between the two will be 8. Now, as this video plays, if you were to find the difference between those two distances where the focal point and the point on the curve and the point on the curve and the second focal point, that answer will still be 8. So that distance is what remains constant. And once you get all the way to infinity, hopefully you'll see that you start making the picture on the other side. And the difference of the distances always stays the same. Hopefully that was a good visual representation of how a hyperbola is actually constructed. So the equation of a hyperbola centered again at any random point h comma k in standard form is divided into two separate functions or two separate equations. You can have a horizontal transverse axis, which means if you think of the two parabola-like shapes for a hyperbola, it's the line that connects the two vertices. So if that line is a horizontal line, then we call it a horizontal transverse axis. And if it's a vertical line, because the two pieces are on top of each other and the vertices have to be connected with a vertical line, then we call that a vertical transverse axis. So if the transverse axis is horizontal, then we use this first equation. It's the exact same thing as that of an ellipse, but with a minus in the middle. Now, hopefully you remember for an ellipse, when we changed the major axis from a horizontal to a vertical, the denominators were what switched places. For hyperbolas, it's the numerators that switch places when we go from a horizontal transverse axis to a vertical transverse axis. Notice that a squared stay the same spot, b squared stay in the same spot. X minus h, the quantity squared, changes to y minus k, the quantity squared, and vice versa here. Now, vertices are always going to be h comma k plus the distance from the vertex to the center. And then the focal point is also going to be the same thing. The center plus the distance from, plus c, where c is calculated as c squared equals a squared plus b squared. Another point of difference between ellipses and hyperbolas: with ellipses, this formula was a squared minus b squared, whereas with hyperbolas is c squared equals a squared plus b squared. So let's take a look at a couple of examples here. If we have an equation, x squared over 9 minus y squared over 1 equals 1, and we're trying to find the oblique asymptotes for this function, we can do so by solving for y, approximating what we get, and then finding the square root. So first thing we do is we solve for y squared. We can do that by moving this x squared over 9 over to the other side and getting negative y squared equals 1 minus x squared over 9. We can multiply all the terms by a negative 1, so all the signs will switch. And then in order to get rid of the square, we can use the square root property to get plus or minus the square root of x squared over 9 minus 1. Now, here's where the approximation comes in. If we're thinking about a really, really, really large number for x, so let's say 1 billion. If you square 1 billion, you're going to get a big number. When you divide it by 9, you're still going to be a massive number. Now, if that's how much money you have, and I say, hey, can I borrow $1? Is that really going to affect your life? If you have 1 billion times $1 billion and you divide it by 9, you still have a boat ton of money. And if you just give me $1, it's not going to change your life at all. So we say that approximately this function is equal to the square root of x squared over 9 without the minus 1. Because the minus 1 isn't really going to do much as x gets very, very large. And now this last part comes in. So find the root. What that means is square root of x squared will just be x. Square root of 9 will be 3. We have plus or minus because we're using the square root property. So this means that there are going to be two oblique asymptotes that the function has to respect. Y equals x over 3, positive x over 3. And then the second equation will be y equals negative x over 3. Now that we have all this information, we can start graphing the function. The center is at 0, 0. We see that x is not being translated anywhere, y is not being translated anywhere. So the origin is where the center is. The vertices are going to be a distance of a away from the center. A is the square root of 9. It's the larger number, so it's 3. So a is 3, so I add 3, move to the right. I subtract 3, move to the left. Now, how do we know that we have to go left to right as opposed to up and down? The larger number is underneath the x term. So that's where the major axis is, which means it's a horizontal major axis. B is 1, so you can go up 1 and you can go down 1. Well, I'll talk about this box in a bit. The focal point, or the focal distance, is c squared equals a squared plus b squared. Well, a squared plus b squared is just going to be 10, 9 plus 1. And then when you take the square root of that, you're going to get plus or minus the square root of 10. So that's what c is. So from the center, if we go to the right by square root of 10, so again, think about it. If the square root of 9 is 3, the square root of 10 has to be a tad more than 3, right? So if we were to add square root of 10 to 0, you're going to go a little bit to the right of 3. And if we subtract square root of 10 from 0, we're going to get to a little bit to the left of negative 3. The parabolas have to, not the parabola, sorry, the hyperbolas have to extend but never, ever, ever touch or cross the oblique asymptotes. So they open sideways like so. Now, this box that's created in the middle, you'll notice that the points of intersection of the box are always on the oblique asymptotes. That should be the case, and if it's not, then somewhere along the way you made a mistake. The width of this box is 2a. The height of this box is 2b. So the distance from the center to the vertex is a. The distance from the center to the top of this box or to the bottom of this box is b. Total distance would be 2b. So we can generalize finding the oblique asymptote equations as if we have a transverse axis that's horizontal, then it's going to look like y minus k equals plus or minus b over a. The minor axis over the major axis divided by 2 times x minus h. And if we have a vertical transverse axis, it's going to be the same equation, except it's going to be the reciprocal of b over a, and that's going to give us a over b. Sorry about this. I'm not sure why there's an overlap here, but here's a general picture of a hyperbola. So a center at h comma k. If you go a little bit to the left, you get to the vertex, so that's a distance of a. If you go to the right and you get to the other vertex, that's a distance of a as well. If you go further to the left, you're going to get to the focal point. If you go further to the right, you're going to get to the focal point as well. If you make a line, a vertical line, or a line that's perpendicular to the transverse axis that passes through the vertex, you're always going to intersect the oblique asymptotes. Same thing on the other side as well. If we make a vertical line that's perpendicular to the horizontal transverse axis, we're going to intersect in the two oblique asymptotes. That's always going to be the case. And if that's not the case, then again, go back, check your work. Maybe your graph is wrong, maybe your algebra is wrong, but somewhere along the way, there's a mistake that has happened that needs to be rectified. Here, we have a graphing question. So let's say we have to graph y minus 2, the quantity squared, over 25 minus x minus 1, the quantity squared, all over 4 equals 1. Let's say we have to find, sorry, this is getting hard to read. Let me just toss this equation. Much better. All right, so the center is at 1 comma 2, h comma k. We know that this hyperbola has a vertical transverse axis because the y term is first. Had the x term been first, that would have been a horizontal transverse axis. A squared is 25, so I know that a is 5. B squared is 4, so I know that b is 2. So with this, we can look at finding c first before we move on to graphing it. C squared must be a squared plus b squared. 25 plus 4 is 29. And then using the square root property, c turns out to be plus or minus the square root of 29. Now, because this is a vertical transverse axis, we're going to move the vertex up or down to get to we're going to move the center up or down to get to the vertices. So if we take the coordinates for the center, 1 comma 2, in order to move up and down, we have to add and subtract 5, or a, from the y coordinate so that we go up or down. That's going to give us 2 points, 1 comma 7 and 1 comma negative 3. For the focal point, we do the exact same thing. For the foci, we do the exact same thing. We take the y-coordinate, add root 29 or c to it, and then we subtract root 29 or c from it. The oblique asymptotes, because this is a vertical transverse axis, are going to be y minus 2 equals plus or minus a, which is 5, over b, which is 2, times the quantity x minus 1. Now, had this been a horizontal transverse axis, the equations for the oblique asymptotes would be the same. They would just be flipped. The slope would be flipped. So this would be 2 over 5, b over a. Well, graphing this function is relatively simple as long as you do it in pieces. You build up from the middle out. So you first plot your center, 1 comma 2. Then you plot your vertices, 1 comma 7 and 1 comma negative 3. Then you plot your focal points, 1 comma 2 plus root 29, I think, and 1 comma 2 minus root 29. So a little bit past negative 3 and a little bit past 7 here. Next thing, we can graph our oblique asymptote. So first oblique asymptote looks like so. The second one with a negative slope looks like that. And at this stage, we're basically done. You can just draw your function to make sure that you respect your asymptotes on top and on the bottom. And if you connect these dots, even in a rough manner, you see that you do form this box where the lines, the vertices of the box intersect or lay on top of the oblique asymptotes. As a last example, let's say we're asked to graph 9x squared minus y squared plus 2y equals 10. So again, whenever we're given the general form, we always have to complete the square in order to get it to standard form. And to do that, we need to remember that the leading coefficient must be 1. It can't be negative 1. It has to be positive 1, or just 1. So there are no other x terms, so we're just going to leave 9x squared, and it's just going to keep coming along for the ride. We're not touching it. For these last two terms, we can factor out a negative and get y squared minus 2y. Again, we're doing this so that the leading term here has a positive coefficient. Now we divide the middle term, the coefficient, by 2. So 2 divided by 2 would be 1. Square it. Well, that's going to give you 1 as well. So as we've done many, many times now, we add 1, we subtract 1 to keep the problem the same. Then we peel off this last 1 and we keep it by itself. We distribute the negative 1 to it. Negative times a negative will make a positive. 9x squared is just going to come along for the ride. And this is a perfect square, so it factors into y minus 1, the quantity squared. Again, you'll notice the 10 just comes along for the ride. We're not really doing much with the 10 at all. At this stage, we can take the plus 1 that was here, move it over to the right-hand side, and make it a 10 minus 1, which is going to give us a 9. Now, remember that the equation in standard form for a hyperbola always has to have a 1 on one side of the equation. It can't have anything other than that. The only way to get rid of the 9 would be to divide it out. So if we divide each term of this equation by 9, these two 9s are going to cancel, leaving behind just x squared or x squared over 1. Here you're going to be left with y minus 1, the quantity squared, all over 9 equals 9 divided by 9 would give us a 1. So this is the equation in standard form for a hyperbola. Since the x term is positive, we know that this is going to be a horizontal transverse axis. We know that the center is at 0, negative 1. A is the square root of this number, so that's 1. B is the square root of this number, that's 3. If we know what a and b are, we can find what c is by using a squared plus b squared, which is 1 plus 9, which is 10. Take the square root of both sides using the square root property, so you get plus or minus root 10. Again, because we have a horizontal transverse axis, we have to move the vertex or the center to the left or to the right in order to get to the vertex. So we add 1, we subtract 1, which is what a is, and then to find the focal point or the foci, we add root 10 and we subtract root 10. Now, once we have all this information, we can find the oblique asymptotes before we start graphing. And the oblique asymptotes are quite simple. Y minus k, so y minus 1, equals plus or minus, because this is a horizontal transverse axis, b over 1a times the quantity x minus h, where h is 0. So this gives us 3 times x, which is 3x. The negative 1 can be moved over to the other side and get plus or minus 3x plus 1. So this is my first oblique asymptote. This is my second oblique asymptote. My center is at 0, 1. If I move to the left by 1 or move to the right by 1, I get to the vertex. If I move to the left by root 29 and I move to the right by root 29, or sorry, root 10, then I get to those two numbers. These are the focal points. And then as long as I negotiate with and respect the asymptotes, that's my graph on this side, that's my graph on the other side. Last thing to discuss for hyperbolas is their eccentricity. So it works the same way. The formula is still the same, c over a, as it was for hyperbolas. However, or as it was for ellipses. However, there is a point of difference, and a big one. For ellipses, E had to be between 0, which it could hit 0 if it was a perfect circle, or be less than 1. Now, for a hyperbola, it has to be between 1 and infinity. So again, I want you to pause the video, create a bunch of graphs, a bunch of equations, do whatever you need to, play around with it, and determine why it can't be either of those two numbers. Under what circumstances would E be 1? Under what circumstances would E be infinity? So play around with that. It's very, very important to understand edge cases. Why is it that something can't possibly be the case? It's something very, very important to understand in mathematics. Now, as to numerical values of eccentricity, if you're closer to 1, you're closer to the transverse axis. If you're further away from 1, you're further away from the transverse axis. So for both of these, the transverse axis is horizontal. For the one on the left, you are closer to the transverse axis, so the eccentricity is closer to 1. For the one on the right, you're further away from the transverse axis, so the eccentricity is further away from 1. And that's it. Hopefully that made sense. If you have any questions, please feel free to reach out to me on Slack, by email, or better yet, just post a comment on this video. And that way the same question doesn't keep getting asked over and over again. I can just point students or anyone else to just the comment in the video itself. Take care. Have a nice day. We'll see you next time.